Hi, we're back. Notice we're now in chapter 28. We only hit a few topics in chapter 27. And same thing is going to be true for 28. We're only going to hit a few topics in chapter 28. What we're going to get into really is atomic physics. And at the end of this section, you're going to start seeing some things that overlap into what you've probably learned in your chemistry classes about atoms. But I want to start with this mystery that we've already kind of started talking about with the black body radiation, how this curve, this spectrum of black body radiation from the eye of our stove, say, did not fit with what people back in the late 19th century thought light should do. Their own theory predicted a sort of the old conventional classical wave model of light, predicted a spectrum that looked nothing like the spectrum that actually showed up when they heated objects up and looked at the light coming from them. So there was something going on weird with light. And then that problem deepened as the particle-wave duality was discovered, and it was discovered that light, sometimes if you ask certain questions of nature, it would say that light has a wave nature, whereas if you asked nature another question about what light is, it would say light is a particle. Okay, so this particle-wave duality, which sort of made light kind of mysterious. And then de Broglie came around and said, hey, wait, it's not just light that shows this duality of waves and particles. It's kind of both, depending on what question you ask, and how, or rather, it's both depending on how you ask the question, right? If you ask nature, is light a wave, and do one experiment, you get, yeah, it's a wave. If you ask nature another way, is light a wave, you get the answer, no, it's a particle. That this duality applied not just to light, but to matter. And by matter, I mean stuff with mass. Stuff made up of electrons, protons, and neutrons for our money. There's a lot of other ons out there that have mass, but most of the stuff we see around us is composed of those three ons: protons, neutrons, and electrons. And those particles themselves have a wave nature. Therefore, the things that those particles make up, baseballs, your pets, my glasses, the markers, the planet itself, has a wave nature. So what light really was the turn of the 20th century was really at the forefront of physics. And there was another experiment that was done, and the results made no sense whatsoever. Very simple. Fluorescent lights, not in here, these are incandescent, but fluorescent lights like the ones in our lecture room, if you heat up the gas in those and put that light through a spectrometer, it will not be a nice rainbow. Incandescent lights like these are just a plain white light bulb, the old school light bulbs, not the little tubes that we have now, but the ones that they had maybe when y'all were younger, kids, whatever. The old school incandescent light bulbs, if you look at those light bulbs through a spectrum, you get the full rainbow, like the Pink Floyd record cover. Sunlight, you get a full rainbow, almost, but close enough. Right? The rainbows that we see, rainbows, have the whole spectrum. But if you take a tube of some gas, like mercury gas or like hydrogen gas, and light those gases up, as in a fluorescent tube, the spectrum you get when you pass that light through a prism is not a rainbow. If we take a tube, not of sort of like a neon light, a tube full of hydrogen gas. Now really, it's H2, of course, right? H2, but hydrogen. Don't have to worry about. Actually, you don't have to worry about that, because what's going to happen is we're going to end up ripping those molecules up. So hydrogen gas. Okay, and then you put a nice, what we call alternating current across it. That little symbol there is just a way of saying that we're going to have an electric field that points one way, then the other way, then the other way, then the other way, the other way. Inside the gas, electric field's going to oscillate. Up, then down, up and down, up and down. What you get is it lights up. It turns out that lights up. And it is pink, by the way. Okay. You get light from the hydrogen gas. When you put it in a tube and put an alternating electric field, back and forth, it heats it up, it ionizes it, it rips apart the molecules, it ionizes it, and it emits light. And if you take that light and put it through a prism, you don't get a whole rainbow. Okay. What you get on the screen, if we take that light and pass it through a prism, the light that you get on the other side of the prism is not a rainbow. You don't get the whole range of colors. What you get instead is you get one nice bright pink line. You get a sort of a medium blue cyan kind of line. And I don't have purple here. It'd be nice if I did. Don't have purple. But you also get two faint purple lines. You get 4 lines of very precise frequencies, rather wavelengths. Frequencies too, but I'm going to list the wavelengths here. What you get when you run hydrogen light through a prism, not a rainbow, you get one bright light at 656.3 nanometers every time. That's the pink one. The blue one is 486.1 nanometers, and the two dimmer purple ones are at 434.1 nanometers and 410.2 nanometers. You get only 4 very precisely defined colors. And I'm going to include in this week's Moodle page an image of this spectrum for you. Okay? The question at the turn of the century, early 20th century, was why? Why is this happening? What is going on? Why, when we pass this light through a prism, do we see that the light that's leaving this hydrogen gas is composed of only 4 frequencies? Not the whole rainbow, right? This is white light. We get a nice rainbow across the screen here. Every color, from the deepest purple to the deepest red. But here we get only 4 very precisely defined wavelengths. That's all we get. The question is, why? And moreover, if we change the gas, put in helium gas, we get a different combination of colors. We still get a finite set of lines, a finite set of frequencies, wavelengths. We get a finite set of wavelengths, but they're different wavelengths. In fact, every element has its own signature spectrum. Like a thumbprint for a human being. Every human's thumbprint is different. Every element's spectrum is different. It's a different set of colors, different set of wavelengths, that is, and the relative brightnesses of the wavelengths also varies from from element to element. So these are like thumbprints for elements. So we can look at a spectrum. Once you get to know these spectra, you can look at a spectrum and know what element it is. And there's only one element that goes with every spectrum. Okay, so the question is, of course, why? All right, we'll pause here, take a quick break, and we'll have a short video next and say a little bit more about this in the case of hydrogen. Okay.